Okay, now I'm going to continue with uh, the epic question. I may say it's a bit of a long question. So, but I think it involves, it's going to answer quite a number of questions, I guess. Okay, so let's say that we have a pipe of length L, right? And there's a valve here, and this is open to atmosphere, where the pipe diameter is D, and there's a flow here. We don't have a flow meter, and we would like to find the pressure drop here. So we don't have any equipment here which measures the pressure. Therefore, this is open to atmosphere. We can take this as one atmospheric pressure. We would like to find the pressure at this point, let's say. And the pressure drop equation is just after the valve is going to be equal to 2 times fanning friction factor times length times the density of the, I say, water and the mean velocity square. And we are going to assume that it's going to be turbulent flow, and we're going to really see that it's going to be turbulent flow. And here L and D would be measured using different rulers. That different rulers is important. The velocity will be, this G means it's a function, it's going to be a function of, well, how are we going to measure velocity? We are going to collect the typical method for unit operations laboratory students. We are going to collect water in a graduated cylinder at a certain time, and that time will be measured by a stopwatch. And we are going to divide the volume by cross-sectional area by the time it takes to reach a certain level here. Therefore, we are going to be finding the average velocity here. Note that it's going to be average velocity through the pipe. And okay, so therefore we are going to be here this term and this term and this term. So these three terms will be measured. We are going to find this value from the literature, and fanning friction factor will be read from a graph in fluid mechanics course or in different textbooks. You can find how a friction factor, fanning friction factor, changes with respect to Reynolds number. It is an it looks something like this. Depending on the smoothness of the pipe, you have different curves. We are going to be reading friction factor from these figures. Therefore, we are going to be feel the need to find Reynolds number, and in Reynolds number we have average velocity, density, diameter over mu. So additionally, we need mu of this flowing fluid, which is water, and we are going to read that value also from the literature. So three values are going to be basically read, and three variables will be measured, directly measured. So let's start with density. First of all, you should know that density of liquids change with respect to temperature. Now we assume incompressible fluid here, so density is constant with respect to pipe and with respect to different pressure. That's a pretty good assumption because there's not going to be a very high pressure change. On the other hand, note that for instance, density at 21 Celsius is 998 kilograms per meter cube, whereas at 15.6 and 26.7 Celsius, the less significant figures changes. So first of all, if we do not like to take this uncertainty into consideration, we should make sure that we should also measure the temperature here, right? Put a thermometer here, or maybe a thermometer here, or a thermocouple here, wherever, and make sure that temperature is equal or very close to 21 Celsius, because if it's like 5 plus minus 5 Celsius change, there's going to be a small change in density. While the effect on viscosity is much severe, because 15 Celsius and 25 Celsius, you can see that the 10 to the power of minus 3, I'm not going to talk about it, but this number here, it changes from 1.13 to 0.89. So therefore, again, we should make sure that our temperature is close to 2021. Therefore, you can reuse this number again without any uncertainty. If you're not certain about the temperature, you haven't recorded the temperature, then probably you should take the uncertainty of these terms also into consideration. So be careful about that. All right, let's go step by step. We're going to be talking about uncertainty related with each of these measurements. First, let's deal with this collected water in a graduate cylinder step. So let's say that the collected water was for 564 milliliter using a graduate cylinder with a 10 milliliter resolution. Note that this is a pretty much large tall graduate cylinder. Therefore, its resolution is going to be a bit larger resolution of 10 milliliter, because they say its total height is 1 liters. So it's going to be 10, 20, 30 milliliters up to 1000 milliliters, which is 1 liter. Anyway, assuming Gaussian distribution, we can divide 10 milliliters by 6 and we come up with this result. I'm going to go over this resolution and manufacturing a bit faster because we have covered these in the previous lecture. Specification says, they say there is plus minus 1 milliliter accuracy. So BM manufacturing bias is going to be 1/2. We take the score of these values, add them together, and come up with, note that I have written in terms of meter cube, and this here one should be careful about the units, and I'm going to be using SI units, although I start with liter, milliliter, things like that. At the end, I'm going to be using meter, second, and kilograms here, so that there's not going to be any confusion. Okay, so this is the bias square related with volume measurement. Now, time measurement. Let's say that it has taken 3.30 seconds using a stopwatch with a 0.01 second of resolution, which is the usual resolution for stopwatch. So I assume uniform distribution here. I have talked about reasoning about that previously, and I come with a suitable value here. Specification says, okay, 0.01 accuracy. So this is going to be the manufacturing bias, and these two terms will be squared here and added together. On the other hand, I also add another term. It's not exactly a bias term because I stop and start to watch. So previously, if you recall, 0.1 I said here is a kind of a reaction time here, right? So however, this is going to be both at the beginning and at the end. So I'm not talking about this, but note that reaction time itself will change from time to time. So you and probably your friend is filling the graduate cylinder, and you are starting the stopwatch. Think about this not exactly at a constant bias term at the beginning and at the end, but due to the miscoordination of the inescapable miscoordination between you and your friend, it's not going to be exactly, the start time is not going to be equal to when you start to watch, and there's going to be a similar thing when it comes to stopping to watch. So I do not call this 0.1 as the reaction bias, but it's a kind of bias at the beginning and bias at the end due to the absence of perfect coordination, if you say. So I think about in real processes how time passes by, and when I stop it, I think 0.1 second of a bias or an error is pretty good. Actually, to be more realistic, I believe this value is going to be even larger, because if you just visualize in your mind how 0.1 second, 0.2 second goes on, it's not second. Note that this is 1/10 of a second. It goes pretty fast. So to be much more realistic, maybe this value should have been increased to 0.2 or maybe 0.3, something like this. So in this case, whatever the value you put here, we are going to take the square here and add them together. And when we add these values together, note that 0.01 here is much larger compared to those two values. So this reaction time, not reaction time, but the time interval due to the absence of a perfect coordination between you and your friend who fills the graduate cylinder. Well, it's a very long name to say it again and again. So let's say call it a miscoordination error, uncoordinated error, miscoordination. There's not a word like this, I guess. Okay, uncoordination error is this one, squared form. It's much higher compared to manufacturing and resolution uncertainty values. So we find another value. Actually, it's so large that these values make no contribution to the result when I approximate this as 3 significant figures. So it's 0.01 because these are very low numbers. Actually, this is what I did here. The number that you see here, which is 10,000 times 10 to the power minus 6, is indeed equal to this value. I have equated them, all of them, to the 10 to the power minus 6 so that I can add them together. And as you can see, it's a very small number. It's like 30 or something compared to 10,000 is nothing. So let's continue. We measure the diameter of the tube or the pipe in which water is flowing, and we use a ruler with 0.1 centimeter of resolution, and these are the calculations, uncertainty calculations. Like most of the previous cases, the contribution of resolution to uncertainty is higher compared to the manufacturing error. And when it comes to length of this tube or pipe, I am using a different ruler. This time the resolution is 1 centimeter because this is a longer one. So it's divided into 1 centimeter intervals compared to, for the diameter, we had a smaller ruler here, or even much more smaller with 0.1, I guess, centimeters of resolution, 1 millimeter resolution. Anyway, so a different ruler is used. You may ask why I specify this different ruler point. Would anything change if we had used the same ruler? Let's say that we had such a ruler such that you can measure both of them pretty much accurately. Let's say both of these, the diameter and length. So it's not a practical problem that we have here. Yes, there's going to be a difference in uncertainty calculations, which I'm going to talk about in the next example. All right, so the uncertainty calculation, let's say this is the uncertainty related with that ruler, and we find the result here again. All right, so what we have found was length, diameter, we have found density, we haven't found velocity here. Now one may ask this question, since velocity is indeed a function of volume connected area of the pipe, cross-section area of the pipe, and time it took to collect the water inside the graduate cylinder, do I need to specify another variable related with this? So let me give you a hint or a practical method. If we didn't have fanning friction factor here, right, if the equation were like that, it would be a better approach to replace u by v square, a square, and a square is going to be p d square over, let me leave this square here. First, let me deal with u. PD square over 4 is area, and there's going to be time. Then I would put a square here. Then I would have diameter and density. And I don't have any, well, if you have constant, put anything here. We don't have fanning friction factor. That would be better to write in this form, find the pressure drop, and then use the Taylor's expansions first term to find the partial derivative of delta P with respect to L, D, here and here, volume, and T. Then the question would be about, and note that, yeah, there would be 4 variables: length, diameter, volume, and T. Yeah. However, note that, so if you have some complicated equations, try to reduce the terms, try to get rid of those intermediate terms. However, here fanning fraction factor depends on Reynolds number and it depends on velocity. So what I do is I deal with this u specifically or separately, I may say. Therefore, what I do is I first find the average velocity, and I'm going to find the corresponding uncertainty related with velocity. So let's compute velocity here. The average velocity is going to be volume connected area T, a cross section area. This equation, so 4 is here. So when you put the values here, we find the average velocity to be equal to 1.2 or 1.3 meters per second. Now, the uncertainty related with, or it's better to say bias related with velocity. So since this is the equation at hand, I'm going to take the partial derivatives with respect to volume of water collected, diameter of pipe, and also time seen in the stopwatch. So this is the equation at hand, and I'm going to multiply by the corresponding bias values for each of these terms. Hopefully, I have found all of them. So what we do is, for instance, let me talk just the first part of that. When you take the derivative with respect to v here, this is going to be just 1 over these terms. Or in other terms, to be much more practical, it's going to be u over v. So the derivative with respect to v is going to be equal to u over v. If you like, you can use this one. If you like, you can use this one. Note that these two are the same. Because we don't have v here, therefore it means that average u is divided by v. So I put the equilibrium values, which here means equilibrium corresponds to the measured values here, the measured value e and t here. Or if I use this equation, I would have used the measured value of u, or the computed value of u, I'm sorry, here, divided by v. Now, one thing that may favor this approach is, note that here there's going to be a rounding off, and there's going to be a rounding off error when you divide by v here. So it's a better idea to use this term here, numerically at least. So you do the same thing for these terms, and I come up with, I'm going to skip those, you can easily see them here. So the contributions here to velocity consist of these 3 terms. Now, when you look here, you can see that the volume measured as a very small contribution compared to those two. So just at this point, one should realize that in order to obtain a better measurement, a more reliable measurement for average velocity, you should more concentrate on the diameter of the tube or pipe measurement, and also time measurement here. Which one was the time? Yeah, this is related with time measurement, I guess, and this is related with diameter of the pipe measurement. So this is the bias square related with u, and bias is square root of that value, and I find the as if this is the final thing that I would like to compute, I found the point estimate and the corresponding bias term. Therefore, we have about 6% uncertainty in average velocity value. All right. Now we also handled this. So at this point, I can easily take the partial derivative with respect to u here. I don't need to separate u into different terms. Now we have f here, which is the most problematic thing because we have a reading from the graph. So what we are going to do is we are going to use this expression because f is a function of Reynolds number. As I said, I'm going to show you. We have a fanning friction factor versus Reynolds number graph, and Reynolds number consists of these terms. So now, so if I write this whole thing like this, the pressure, the bias in pressure drop is going to be the partial derivative with respect to f, partial derivative with respect to u, d, and l. So what did I do here? Actually I have come to this equation. In order to find the bias here, I'm going to take the partial derivative with respect to f, l, d, and u. 4 terms, since this I assume it is without uncertainty here. So these are all found, right? The partial derivatives are easy to find, and the bias terms are also found. Partial derivative here is going to be, again, very easy. It's going to be 2 times LD all the terms except this one, but we need an BF square term. So that's what I did here. What we need to find is this. What is the squared bias term or bias term itself for fanning friction factor? So once I have written this, and I note that I have found all of these above, right? And these are going to be easily obtained from the equation. Well, it is easily, but it's a little bit of a long procedure, but it's a straightforward procedure. Now, this is, let's go into the meaning of that before diving into the partial derivatives. It is simply how much uncertainty are we going to expect in friction factor due to a different or the uncertainties in different variables. And let's see what are going to be those variables, since fanning friction factor is a function of Reynolds number. So that's why I write it as G, a function of Reynolds number. I can write this. Theory, and Reynolds number is density over viscosity. Since I assume that these are free uncertainty, so uncertainty in U and D will be reflected in Reynolds number, and that change or the uncertainty Reynolds number will affect F. This is how this whole thing goes. First, once you understand this, it's very easy to go with the mathematics. So basically, BF square will be the partial derivative of F with respect to U square BU, since this is a Reynolds number, F is indeed, it means is a function of UD. That's what I did here. I get rid of this Reynolds number here to see the whole thing more clearly. Plus fanning friction factor divided by partial derivative of fanning friction factor by diameter, again square and BD square. Now there is another thing. I added another thing here. I called it BR square, whatever you would like to call it. It is related with the resolution of the figure. Note that the result F here are going to be reading from a figure, so you need to add something related with also resolution. How much precise can you see the figure or read the figure here? Fanning friction factor number figure. And there is another thing actually also, but here I have omitted this one. This is also related with the smoothness of the pipe. This is not a single curve. I'm going to show it in a minute, I hope. But you should usually assume some E value for the smoothness of the pipe. So depending on the smoothness, we have of these different curves here. So they are in a band actually, not a single curve like this. Therefore, you need also maybe include this factor. For the time being, I haven't included here because there is already too much detail. Now let me show you the figure. Okay, this is the this figure shows how fanning friction factor changes with respect to Reynolds number here. So, or maybe first I will talk about how to read this figure. Actually, it's pretty much simple, but then I'm going to come to these derivatives. Okay, when we put the density value here, velocity and diameter of the pipe and viscosity value, we find the Reynolds number to be equal to 16,700 values. So therefore, it's going to be somewhere here, I guess. Right? Yeah. Now, depending on the smoothness, I don't know whether you can see it. We have some smoothness values here. We can use some smoothness value. Let's say that the smoothness value is, do I have a calculation for that here? I cannot exactly remember, but let's say that you have, what do we have here? Okay, glass, then, okay. Let's say that your smoothness value corresponds to a value something like this. So in this curve will be applicable. So our value is going to be, I guess, somewhere here. Note that here the uncertainty or the width of the curve is pretty much small, but if you were here, then we would have a larger uncertainty, pretty much maybe a larger uncertainty due to relative pipe roughness. So our F value is going to be, so the F value that I have read was equal to 0.028. All right, now, so this equation simply says that BF is equal to those addition of those three terms, and this related resolution I'm going to leave here now. So this part actually says that the bias due to U here. So here, this is simple. What we do not know is how fanning friction factor changes with respect to velocity. So instead of this term, all right, how fanning friction factor changes with respect to Reynolds number, and why did it come from? Okay, how fanning friction factor changes with respect to Reynolds number, how Reynolds number changes with respect to U times BU. Therefore, it's just chain application of chain rules. If you multiply those two, those Reynolds number, partial derivative Reynolds number will cancel, so it's going to be this expression. Now, this part is basically, if we had an analytic expression, that would be very easy. We can directly find the derivative here. But unfortunately here, for instance, there is no expression. Well, there is an expression for the relation between fanning friction factor and Reynolds number, but here the aim of this example is not to use that one, but to use graphical procedures. This should be read from the graph. And this part simply says how Reynolds number changes with respect to velocity. Therefore, it is very easy. This is Reynolds number. So if you take the derivative with respect to U, it's going to be equal to U times D times mu. This is the uncertainty in U, right? Now, I would like you to understand the meaning of that. This is basically delta Reynolds number, a change in or perturbation or uncertainty in Reynolds number. So the uncertainty in velocity is transmitted to uncertainty in Reynolds number. So the computation is very easy because we know bias of U, and we know what this partial derivative is equal to, is density times diameter over viscosity, and this is going to be the change in Reynolds number. And this basically shows, when you multiply those, how change in Reynolds number is affected as a change in fanning friction factor. Basically, it means this. Yeah, I should use the cursor. All right. If this is delta Reynolds number, the change, the perturbation or uncertainty in Reynolds number, then the uncertainty in friction factor is going to be, if you can draw a straight line, is going to be the difference between this red line here and this yellow line here. This is going to be the uncertainty in friction factor. That's what it means from that derivative, the meaning of the derivative. Therefore, the calculation, so the whole thing is going to be, the whole expression is going to be delta F, change in fanning friction factor due to a perturbation in U. That's how I show it. And the second, if you use the same logic using here for diameter, this expression will be equal to change in fanning friction factor due to diameter. The only thing that's going to change here is the inside the expression is going to be the partial derivative of Reynolds number with respect to diameter. So in this case, the Reynolds number diameter derivative is going to be taken in this way. So the partial derivative is going to be equal to density times U times over viscosity. Therefore, the whole fanning friction factor bias would be equal to, without taking this resolution into consideration for the time being, because they have got nothing to do with these computations, is going to be the addition of those two. It's not fanning friction factor. This is I'm sorry, the fanning friction factor, of course. This is delta fanning friction factor squared due to the uncertainty in U, and delta fanning friction factor squared due to the uncertainty in D. And how do we compute those? As I said, I need to take the partial derivative of U. I take the partial derivative of U, and I have BU here. And when I multiply those two, I find that we have an uncertainty of 923 units due to in Reynolds number due to U, due to uncertainty in U. So a perturbation in U in the reasonable range that we have suggested would yield a perturbation about 1000 units in Reynolds number. But actually Reynolds number is unitless, so we should say I should, let me correct myself, no unit, unitless change of 1000 unitless, like no name, in Reynolds number. So basically we have calculated this part. So the uncertainty in U will result a 1000, about 1000 change in U in Reynolds number. So now the question is, if we should go back to the graph, if you move around the point that you measure 1000 units either to the left or to the right, actually we assume it's going to be symmetric because we assume it's going to, we are in a linear regime. Well, in reality it's not going to be so, but anyway, so 1000 units change is going to make a very small difference, but try to come up with ruler or a more precise instrument. Try to come up with an estimate here of how much friction would change. And my estimate for this case was, let's see, so it's 0.028, let's say that value. So I assume that that value would be equal to 0.001. So from 28 to 27, it would drop down, or maybe it would increase to 0.029. So the change is going to be 0.01. So I take this value as the bias here related to fanning friction factor due to uncertainty in U. And doing the same calculation, this time for diameter, I obtain a change of 390 unitless Reynolds number, and this roughly corresponds to 0.0005 of fanning friction factor. Now comes the resolution. I assume that, well, it's not assumption, but it's actually, as you can see, we have a resolution of 0.01 units here, right? The region where I made my reading. And therefore I divide it by 6 again using normal distribution assumption, and I come with those results. And this comes with the highest contribution here. On the other hand, I'm a little bit of skeptical whether this 0.01 should be exactly obtained, because you are probably going to be using a ruler for that region, and that ruler is going to be a better representation here, or is going to be have a higher resolution. On the other hand, we have another problem here. Note that this is a logarithmic ruler here, so it's not going to be very easy for you to read, to make an accurate reading between 0.2 and 0.3 using a regular ruler here. So I'm not very comfortable with that 0.01 resolution. I think this should have been slightly more lower, maybe 0.05, something like this. But there is going to be an uncertainty related with that reading. I'm pretty much sure of that, because it is logarithmic and also it doesn't have units. So when you use a ruler, there's going to be some uncertainties. Anyway, so we have found the uncertainty related with fanning friction factor using this method. So what I basically did is I have looked at my x-axis. My y-axis is fanning friction factor. Whatever the x-axis is, if it were if fanning friction factor in that graph depended on velocity, then I would have only taken partial derivative to velocity and do the calculation. That would be pretty much easy. How much velocity can change? So irrespective of that change, just interpolate and see how much fanning friction factor or that variable on y would have changed. But here it fanning friction factor dependent on another variable, which is Reynolds number, and Reynolds number dependent on U and diameter. So I have taken the concentrations, or I have taken in the uncertainty of U and D at the same time. So now we complete the calculations. Now we find delta P, which is going to be our point estimate, which is equal to 8,389 Newton per meter square, or Pascal. Basically, it's about 804,000 pascals. So it's a pretty much low pressure drop compared to atmospheric pressure. Then what we do is I find the partial pressure with respect to each of these variables I talked about: fanning friction factor, average velocity, and what else, diameter and length. And I multiply, after squaring these partial derivatives, I multiply with the squared bias of these terms, and I have computed all of them previously. When I do that, I can easily find the resulting values. All right, here I find the B square value. Note that it's a good idea to compare the magnitudes here. All right, so this is 10 to the power 5, this is 10 to the power 6 and 4, and this is very small. Now the uncertainty due to uncertainty in length is very small. Due to uncertainty in diameter here, if you take into consideration only diameter, it doesn't seem to be very high. Now velocity seems to be a very important factor, but if you go back to velocity, why velocity, the uncertainty of velocity, what does it depend on? It particularly depends on diameter and temperature. I'm sorry, time. So diameter and time readings are pretty much important to determine a correct velocity. Fanning friction factor as effect in terms of uncertainty close to velocity, slightly lower than that. But if you recall, fanning friction factor also depends velocity and diameter. So again, we have diameter here, and we have diameter also which affects the velocity. So all in all, this uncertainty, the resulting uncertainty, okay, I'm going to find this number, take the square root, then multiply by 2, and I find a pretty much large uncertainty value. I don't know whether I didn't have, but there is like a 34% of uncertainty is going to be in my experiment. Now, what was I saying? I was saying that this analysis shows that if you would like to reduce this uncertainty, right? Let's say that you would like to make sure that the pressure drop is less than 10,000 pascals. Well, seeing this result, you cannot make sure that this is going to be the case because there is a large uncertainty. At this value, it exceeds 10,000. If you really, for the sake of the question, would like to make sure that this is the case, then you should make your experiment more precise. And in order to do that, this whole analysis says that it's not sufficient to say, okay, do the experiment with better equipment or with more carefully. You should especially concentrate on these two. Now, concentrating on time is a bit of a difficult issue because most of the uncertainty in time comes from the lack of coordination between the two members of the group, and I don't know whether this can be, how it can be improved, maybe by practice. But here the measuring of the diameter of the pipe, it seems to be the most important step, and this step can be the quality of the measurement can be improved using a more accurate and a more precise measurement using a more accurate ruler. So you should be much more careful with those ticks on the ruler, and the accuracy of the and also resolution of the ruler should be much higher. Now, the very nice thing about uncertainty analysis, although this is a pretty much long procedure, but actually there are some computer packages, as I said, which you may use. These calculations are, I have just made up these values. Well, actually, of course, the experimental values are made up, but you could have easily come up with this length, diameter, and volume collected and time. The rest of the values are, I collected those using the internet, using the specifications of some of the graduate cylinders and stopwatch, things like that. And the other values and the resolution was again related to those equipment, which are like educated guesses or due to experience. All of the other things are, or most of them were educated guesses. So using some educated guesses and on an experimental data, nothing else is required, you can come up with which of the steps seem to be the most crucial to improve the accuracy, to lessen the uncertainty in an experiment. So that's and also to improve the accuracy and precision if you can. Well, here we had no repetition of the experiment. If there were repetition of the experiment, then this bias square would have been added to also a p-square, which comes from the precision of the experiment, which is related with the precision of the experiment, which is due to repetition, and uncertainty value would have been even larger to include the real value. Okay, so that's that epic question, I may say. Now I'm going to talk about two more questions. They are going to be very short. Now one is very simple procedure. You have let's say petroleum product. It is let's say it's pretty much viscous, and it has a very high boiling point, and there is some water here, and or something else. Well, in this case, these two phases would be immiscible. Let's say that there is another thing here which has a high boiling point, and we have water here also. They form as a mixture. We would like to get rid of water, so what we do is we just boil water, right? Before boiling, we measure the weight here, so it's going to be that component A, liquid component A plus water. Then we get rid of water by boiling. Then we measure again, so the result is going to be the mass of the resulting liquid. So assuming that only water is lost during this boiling procedure, I would like to estimate the mass of the water at the beginning. So a very simple procedure. It's going to be mass total here at the beginning, and I also neglect the mass of the container here. Mass total is going to be subtracted from the mass liquid at the end. The difference is going to be mass vapor or mass water. So I simply call it vapor is equal to total minus liquid thing. Actually, it's a very simple experiment. Now, what is going to be the uncertainty in this V? This is the question at hand. You can say that we here find the mass here, right? M total and M liquid here. Relating to that M total, we have due to the limited significant number of figures here, we have a resolution. And then due to the manufacturing bias, there's going to be bias coming from the manufacturing. And it's the same thing here. Then it's going to be just the partial derivatives. Here it's going to be partial derivative 1. This is going to be -1, but when you square them, it's going to be all of them 1. So basically, we are going to take the square of bias here, square of bias here, add them together. The result is going to be square bias in mass of water. Actually, it's not going to be so. The reason is because this, if bias of MV, I may say square, total square plus bias of L square, let me just say V square. This expression is actually based on the assumption of independence of these two terms, and also independence of these two uncertainty terms related with those two measurements. If I am using from the same brand two different lab balances, that would be the case. if I'm using the same lab balance on the other hand, whatever the bias of that manufacturing bias related with that balance is going to be the same here. So when you actually subtract those two, you can intuitively realize that those two bias terms will be canceled. So therefore, in much more formal terms, it's going to be like this. Bias square is going to be equal to, since partial derivatives are 1 and minus 1 here, so it's and minus 1 and 1 square, they are going to be 1. That's why I didn't consider that. So it's going to be the bias of this, bias square of that term. So it's going to be bias, I call this, which is going to be total mass, due to manufacturing and due to resolution. So this part. And this step is going to be the subscript L and T correspond to which stage we are doing the weighting process. Again, manufacturing and resolution. Now here is the interesting point. These two are equal to each other. These two are also equal to each other, right? Because they have this, they are the same equipment, so the resolution is going to be the same. On the other hand, these two are independent from each other because at two different instances, you measure the resolution. Although the resolution bias is going to be identical, these are separate measurements. So whatever, let's say that the real mass is 8.0.57, and this has been rounded up to 78.1 grams. And for this one, let's say this is 100, or let's say this for the second step is going to be smaller. 50 I'm just making up 50.67 grams. So this is rounded up to 60.7 grams. Now for both cases, there's going to be a 0.1 gram of resolution. Resolution is going to be like this, but the rounding of here and here, because these values are independent from each other. So whatever the bias here in the first step in terms of resolution is going to be independent from the second. But on the other hand, when it comes to manufacturing, not only these two values are equal to each other, the values themselves are also equal to each other. Let me put it that way to make it much more understandable. BT, indeed BT, I have also mentioned that here, BTR square is equal to, it's statistically it's equal to, expected value are equal to LR. On the other hand, BTR is not necessarily equal to BLR for a specific case. On the other hand, for this case, not only BTM square expected values are equal to each other, but also as an individual value, which we will never know, they are going to be equal to each other. Therefore, I also need the covariance terms here. Just go back to the previous lecture. You are going to see that the covariance term is going to be added as -2 because we have minus sign between them, times the first bias and the second bias terms. And since these bias terms are equal to each other, it's going to be BM squared simply, -2 BM squared. They are going to cancel these three terms. And the result is going to be bias will be only due to resolution, but it's going to be 2 times resolution because we repeat the experiment. We do the experiment 2 times. And this also comes from, if you look here from this perspective, but since we subtract these mass values, the bias from both for the machine will cancel each other. And the result will be free of bias since we find the resulting mass here. On the other hand, there are going to be 2 uncertainty terms equal to each other due to resolution. Therefore, the result is going to be 2BR squared. So BR is found here like this. Take the square. You can go over this computation. It's pretty much easy. and then we find the uncertainty, and I should have multiplied somewhere here. Yeah, going from this step to the step, I multiplied, right? 0 by 2. This is the result that we obtain. Note that if we had an operation which needs adding the mass values using the same weight, these are not cars, these are our lab scale using different masses, then we are going to add those masses, let's say, in our computation. Then the uncertainties will be added. Basically, this minus sign would have been a plus sign due to addition. So there is going to be the effect of bias is going to increase more and more. So if you add those masses or whatever, if you have an additional operation, then bias effect, and you're using the same equipment, then that bias due to manufacturing is going to have a much more, a bigger problem. And you can realize that in your mind. Think about it. Whatever the mistake, whatever the error committed for the first weight, the same amount of error will be committed for the second weight, and the same amount of weight will be committed by the third weight. And when you theoretically add those weight values, basically you commit the same error related with accuracy 3 times. So it's going to be a more problematic result here. Now comes the final question I would like to solve. Well, actually, I'm going to talk about linear regression and calibration charts later, and uncertainty due to interpolation or taking numerical derivative. For this example, I'm using a very simple chart here. Let's say that we have for hydrogen gas, we have this following data. Cp at various temperature values, right? And we are interested in determining the uncertainty related with, of course, we are going to, Cp is not going to be usually a final result in your experiment. It may be probably an intermediate result, but we would like to determine the bias term related with Cp. And Cp is going to be read from this table. And let's say that we need to find, we have to 320 Celsius, this experiment is conducted with, of course, some uncertainty. And we would like to see how this uncertainty in temperature is reflected. And what's that uncertainty? Let's say that the uncertainty is 3 Celsius. So plus minus 3 Celsius. There's an uncertainty in temperature. How is this going to be reflected in Cp? Usually what we do is between 300, since this value falls, this 320 falls between 300 and 350, we take these two values and interpolate. Now, so it's going to be 300. It's here, let's say 350. It's here. What we do is we plot these two points and we interpolate here. It means draw a straight line between those two. And wherever that 320 falls, the corresponding Cp value will be read. This is used usually for point estimate of Cp. So if we basically do that, it's going to be corresponding to those two temperature values, Cp at 14.427 is Cp at 350 Celsius, and at 300 Celsius is 14.07. It's 14 point. Well, I wrote them in a little funny way because I erased something here, and we divide by 50, which is the temperature difference. Therefore, this is going to be the slope of that straight line. So if you multiply the slope of the straight line by 20, 20 is that the difference between 320 and 300, and then add the lowest value here, which is equal to this is going to be 307. All right, the result is going to be equal to this 14.05, 355. So now first, what is the uncertainty related with that? First, let's keep the problem simple. Just these 2 points, let's concentrate on. Do not please see the other points related to CP versus temperature. There may be a change in temperature, there perturbation or uncertainty in temperature. Indeed, there is plus minus 3 Celsius. How is that going to be reflected in CP? That's very easy. It means this could have been easily 323 or 317, it means. Therefore, if you take one part here, it's going to be basically a change would be like this. So the uncertainty related with CP is going to be equal to this part. Therefore, this is going to be simply equal to this slope multiplied by this value. And note that this is again using the equation because CP is, or this function itself is a linear function. And here we assume that CP is equal to A times BT here. Therefore, CP T is equal to B here, this slope. What we do is we multiply this slope using delta T value, which is actually the uncertainty in T, if I can write it. And that's all. So since we have found the slope already, which is 0.024, a couple of more zeros, by 3, this is the uncertainty related with temperature. So you can easily take the square here. So therefore, this is going to be easily equal to uncertainty in CP. On the other hand, note that interpolation itself, only using these 2 points, is a model approximation. Here, we do not take any other point, right, to find the relation between CP and T. Therefore, this is the model that we assume for the relation between CP and T. And if you go back to the previous lecture, one of the reasons for uncertainty is also model process inadequacy, or a model and a process are not consistent with each other. So there's going to be an uncertainty due to model process mismatch. So here, if you also include other points, a couple of more points, a curve like this looks better, more reasonable than I may say. So the question that we need to answer right now is, if we had taken, if the relation here is not linear but something else, and probably it's something else because it doesn't seem to be linear, but actually it's not a very good representation. Let me show it by using MATLAB. Okay, on MATLAB I have the data at hand, so let me show you. I'm sorry, this is not the one. On MATLAB, I have concentration, CP and temperature. The first 5 observations, not the observations, the first data points I have. So I have these, from 250 Celsius to 450 Celsius. Though I'm interested in this interval here, I have included 3 other points, just to see the general trend. So if I plot these, all right, this is what we have. As you can see, the whole trend is hardly linear. Therefore, since the whole trend is non-linear, actually seems like maybe a quadratic fit, maybe good or maybe higher order. Indeed, it was, I think, a third order fit I fitted to this graph I'm going to show right now. Actually, an exponential fit would have been even better, but I would like to continue with simple curves. Anyway, the moral of the story is between 300 and 350, we're going to see whether the linear approximation seems valid or not. So now let's hold on. And here I have Yeah, I think that was third order. It doesn't matter. So actually using those 5 points, you can come up with a good fit instead of a first order one. And this is the one that I have. All right. So it pretty much interplays these points here. That third order effect can be seen here as a change in the second derivative here, as you can see. Here it increases, but from this point on, the second derivative seems to change sign. Anyway, let me also show you, yes, the linear trend. So actually what we do here is in interpolation between 300 and 350. Let me extend this, and maybe a different color would have been nicer, a line style or line width. Okay, between interpolation meaning between 300 and 350 Celsius, we just draw a straight line. Whereas using other points neighboring to that region, we can come up with another polynomial approximation to this curve that we actually do not know. Which one reflects reality better? Actually, I don't know about these experimental points, but assuming sufficient, let me say, smoothness of this curve, of this function, I think this third order will be a better approximation of reality. So in this case, if I indeed concentrate on 300 to 350 region, do that. All right, so 320 is this point here that I predict using my linear fit. On the other hand, if I were to use a third order polynomial, this value would have been here. So this is going to contribute to uncertainty, because different models, fitting different models to the data at hand would result in fitted different predictions of the new point. So how are we going to calculate the uncertainty here? I'm going to give a very practical approach here, simple approach. Use an interpolation like this, and also including the neighboring points, use a little bit of higher polynomial and see whether there's a deviation between these two. And there seems to be a deviation. So find the value at this point, this polynomial equation, whatever it gives here. Actually, I have already calculated this value, or I think I can read it here. Yeah. It is at 320, it is 14.3676, whatever this number of significance figure we take into consideration. So the difference between this value and this predicted value is going to give me an magnitude of the uncertainty. So it's the value that I estimate using the third order polynomial is equal to where is that value? It's going to be 14,368, I guess. I subtract the value, the interpolated value, which is 14.355 from this value, indeed this one, from this one, because in bias calculations, you first write your measured value, then the true value kind of thing. And there is a deviation. I do not indeed say that this is the true value, but this is probably more closer to the true value, I may say. So therefore, it gives me a range between two observations. In order to convert this range to standard deviation, I divide by square root of 2. So you may ask, where does the square root of 2 come from? It's a very simple derivation, which I'm not going to do right now. But if we have two observations from any distribution, and the range between two observations, which is equal to absolute value of x1 minus x2, in this is equal to the sample standard deviation obtained from these two observations, square root of 2. Please prove it. It's very simple arithmetics. You just write the standard deviation equation for two observations. You can see that this is the case. Therefore, I convert this to standard deviation, of course, indeed neglecting the negative value. So I can square this value, then add it to the uncertainty due to temperature. So that is one way, and almost the simplest way of dealing with this model uncertainty. Okay, now the second thing I would like to talk about is the uncertainty in finding the derivative. In some cases, you will be in the experiment, it would be required to determine the derivative at a certain point. So for instance, let's say that if at 220 degrees, we would like to find the derivative of this curve. One option maybe, for instance, just interpolate between those 2 points. So it means actually numerical derivative. If you use only these 2 points here, then the numerical derivative would have been equal to just this slope that we have talked about, slope of this line. On the other hand, if you, again, let me concentrate on that region. On the other hand, at 220, so let me show it with a line. All right, at 220, that would be the derivative if I can show it. Yes, I think this seems slightly better, I hope. Yeah, something like this. I cannot make it better. Actually, you can find it very easily because you are going to have the equation related with this. If you fit a polynomial to the, I think it looks pretty nice now. So line width is equal to 2. Yeah. So if you have all these, you have all these 5 points, and if you fit a polynomial to those 5 points, then try to come up with the derivative at certain points. Then, for instance, the derivative is going to be the slope of this line at 220. If, on the other hand, you use numerical derivative methods and use only 2 points here, then this is going to be your derivative. So let me also use line with 2. So as you can see, the slope of these lines will be different. So one approach may be use both of these methods and find the derivatives here, find the slopes here, and again find the difference between those slopes and take the square and divide by square root of 2, so that it's going to give you an uncertainty in the derivative value that you are going to use in your calculations. So the general idea here is to find the model error related with those uncertainty related to model process mismatch, to use 2 different models and try to come up with a difference that's going to be representative of most of the models that you may be using. Of course, it's not a very valid approach, but for this level, I think it should give you an idea. So one may easily ask the question, is this the true line? Actually, I'm not going to go into details, but I have come up even with a better approximation. Let me also show it to you. All right, I think this is the better approximation. The blue line is the better approximation. Let me focus here. So here, for instance, if we would like to find the derivative at 320, I guess the derivatives are going to be very, very close with the better or the true approximation. But if, let's say, we were to find the derivative at 340, then this line is going to be, let me put it. Oh, that's awful. Yeah, I think that's better. This one seems to the derivative at 340 by by the polynomial method, and this one is the true value, which we will never know. And this is difficult for me to do, but I'll try my best. I think that's okay. So, for instance, this using 2 points here is going to give us a derivative equal to the slope of this line, as you can see, for 340. I'm right now talking about. So let me also draw a line here. So we are talking about the slope which corresponds to 340 Celsius, let's say. So here, using 2 points, give a pretty steep estimate. This polynomial, third order polynomial, gives a less steep estimate. All right, yeah, it seems. Okay, maybe a little bit more like this, no? Like that. Okay. And the blue one, which is the real one, is indeed has the smallest slope here. So if we indeed, we are to, of course, this point is, if we were talking about the corresponding CP value, the true value lies between those two. But here, the real slope is even smaller compared to those two. So it's not going to be included in uncertainty calculation of derivatives. Hopefully, we multiply by 2. So the real derivative at that point will be quite possibly, hopefully, is going to be within the specific or within the specified uncertainty limits. So that's one way to handle the problem. So moral of the story, try to come up with two models, two reasonably distant models here, I may say. One here, for this case, one was a straight linear model found by interpolation, both for interpolation cases and also for finding derivative case. The other one, using a couple of points, come up with a polynomial and see the difference between those two when it comes to finding the corresponding y values and also finding the derivative values, and using the range between those two, the one that you find by using the linear method and also the polynomial method, and division by square root of 2 is a bit arbitrary because that's not a very rigorous method, yet still it seems to work. So it's going to give you an idea about the standard deviation and also the bias or the potential model bias in your calculations. And that's all I would like to talk about, except the linear regression part and the calibration part, hopefully, which I'll talk about in other video.